In this video, we will be creating some more fault handlers, and we will also be creating a keyboard interrupt handler so that we can register when a key on the keyboard has been pressed. Keep in mind that this is a PS2 keyboard handler, so it may not work on computers that do not have PS2 emulation unless you plug in a PS2 keyboard. And no, it's not PlayStation 2, this is PS2, which is the really old specification for keyboards and mice. Alright, so let's get started. Now that we can catch and handle faults, it might be useful to have a panic screen so that we know when the kernel is in a panic mode and can't recover because of a fault, and we can display some debugging information on the screen to help us debug our code. So the first thing we want to do is add a few more functions to basic renderer.h, such as the clear function and the next function. So the clear function will set the entire screen to a single color, and the next function will go to a new line, so we can streamline going to a new line without text. So the first function is void clear, and this takes a uint32t color, and we'll need to include standard int. And the second function will be next, and that just goes to the next line. Now we can jump on over into basic renderer.cpp and write those functions. So the first one is void basic renderer clear uint32t color, and now we need to get the base of the frame buffer, so that's uint64t fb base equals casted to a uint64t target frame buffer base address. Now we need to get the amount of bytes per scan line, so that's the amount of bytes in one row. So that's a uint64t bytes per scan line equals target frame buffer pixels per scan line times 4, because each pixel has 4 bytes inside of it. And then we need to get the height of the frame buffer, so uint64t fb height equals target frame buffer height. And we need to get the size of the frame buffer, so uint64t fb size equals target frame buffer size. Alright, so now we can iterate through every single row in the frame buffer and set the value to the color. So for int vertical scan line equals 0, vertical scan line less than frame buffer height, vertical scan line plus plus. So we'll be doing it row by row. Now we need to calculate the base of the pixel pointer. So that's a uint64t pix pointer base equals the frame buffer base plus bracket bytes per scan line times the vertical scan line. So this will point to the first pixel in every row. Now we do another for loop for uint32t pointer pixel pointer equals casted to a uint32t pointer pixel pointer base. Pixel pointer less than casted to a uint32t pointer bracket pixel pointer base plus bytes per scan line pixel pointer plus plus. And now we can just dereference pixel pointer and set it to color. Alright, so that's our clear function. Just to test that out, we can jump on over into kernel.cpp and remove these page faulting lines, and we can do global renderer clear 0x00 ff0000. So this will set the entire screen to red. Now before we can compile that, we need to create a function for next, or else the compiler will complain. So back in basic renderer.cpp, we can do void basic renderer next. And what this does is just set cursor position dot x to 0 and cursor position dot y plus equals 16. So now if we compile and run that, we can see immediately the entire screen turns red. So our basic renderer clear function is working well. Now that we have that, we can create a panic function so that whenever we get an interrupt that we can't recover from, we can go into a panic screen and display debug information on screen. So to do that, we're going to have to create a few more source files, both of them being called panic, so panic.h and panic.cpp. Inside panic.h, we need to do pragma once. And we need to declare one function, which is the panic function, and this takes a char pointer panic message. Now over in panic.cpp, we can include panic.h, and we can write the implementation for that function. So we can void panic char pointer panic message, and we need to include basic renderer.h. So we can do global renderer clear 0x00ff0000. So we'll set the screen to red. It doesn't have to be red, it can be whichever color you want. We also need to set the cursor position to 0, 0 so that we're writing in the top left of the screen, or set it to wherever you want it to be. It could be halfway down the screen if you want, but I'm going to be setting it to 0, so cursor position equals curly bracket 0, 0. And now we need to set the text color to black so it shows up well on the red background. So global renderer color equals 0. So that'll set all of our color bytes to 0. And now we can print our information. So global renderer print kernel panic global renderer next. And we'll go next twice to make a space in between this line, and then we can do global renderer dot print panic message. Right, now we can go on over into interrupts.cpp and include /panic.h, and instead of printing page fault detected, now we can do panic page fault detected. Now this won't display any debug information yet, so we're going to have to create a string formatting function before we can pass any debug information to the panic screen. But we'll just test this out and see what happens. So jump back into kernel.cpp and put this page faulting code back in and get rid of this call to global renderer clear. We're also going to need to cast this page fault detected to a char pointer, or jump back into panic.h and make it take a const char pointer instead of just a char pointer. So now we can compile and build our image. And as you can see at the top left of the screen, it says kernel panic page fault detected. Eventually we'll have our debug information, as I said, but for now this is okay, just for letting us know that we've got a page fault. Even if it's not everything, it's one step closer to being able to debug our kernel easier. Now we need to create fault handlers for a couple more faults, and this will be the double fault and the general protection fault. They're the next two common faults that we can experience. So back in interrupts.h, we can declare two more functions, so just copy and paste that twice and change page fault to double fault and page fault to GP fault. You can write general protection fault if you want, but this is okay. So double fault occurs when there is two unhandled faults in a row, and the general protection fault happens when, well, there's actually a multitude of reasons why the general protection fault can happen. Here on the OSDev wiki, it says that the general protection fault may occur for various reasons. The most common are segment errors, executing privileged instructions while we're not able to. So there's quite a few reasons, and we'll be able to use the saved instruction pointer to point to the instruction which caused the exception. So we'll print that on the screen in our panic screen, which will help us debug. Alright, so now that we've declared those functions, we can make the bodies for them in interrupts.cpp. We can copy and paste this page fault handler code and just change the names. So double fault handler, double fault detected, and GP fault handler. So general protection fault detected. And we can test these in various ways. So we can test the double fault handler by causing another fault inside of our page fault interrupt handler. So inside page fault detected, we can cause another page fault, which will cause a double fault. So we'll copy and paste that page fault in code and run that, and we should get a double fault. But before we can test that, we're going to need to put these fault handlers into our IDT. So going back into kernel utility.cpp, we can write a new entry for our IDT. So just like before, we can do IDT descriptor entry pointer, or we can just copy all of this because no one wants to write it out again. So change page fault to double fault, and replace all these references to int page fault to int double fault. Change our page fault handler to our double fault handler. And we need to change this IDT offset to the double fault offset, which is, according to the OSDev wiki, 0x8. So we'll change that to 0x8. And we'll do the same with the general protection fault. So int gp fault. Change all those references to int gp fault, and change this double fault handler to gp fault handler. And then we can set our offset to 0xd. Alright, now if we compile and run that, we should get a double fault. Well, actually I was wrong. It's actually creating many page faults over and over again. At the top left, page fault detected is flickering on and off, so it's clearing the screen and running it again. So another way that we can trigger a double fault is by not having a page fault handler at all. So we can remove that. And now, as you can see, we get a double fault. So it wasn't able to catch the page fault, so now we're getting a double fault because it's tried to call the page fault, it couldn't, so it's onto a double fault. Now, a double fault can't be recovered from. The only thing you can do after a double fault is abort, basically. The general protection fault and the page fault can be recovered from, depending on what caused it. So let's uncomment this code here. So interrupts can be used for more than just catching faults. It can be also used for things such as maskable interrupts, and maskable interrupts are things such as the timer chip and the PS2 keyboard and mouse, upon other things. So to get those working, we're going to have to do quite a few functions. The first of which is remapping the PIC chip, which is the programmable interrupt controller. But before we can talk to the PIC chip to remap it, we're going to need some functions to talk to it on the I/O bus. This isn't specific just to the PIC chip, so we'll be able to talk to any device on the I/O bus using these functions. So we're going to need to create some new files called io.h and io.cpp. In io.h we can do pragma once and include standard int, and the functions we're going to create are outb and inb. So void outb, so this is putting a byte onto the I/O bus. So we need a uint16t port, which is selecting the device on the I/O bus to talk to, and a uint8 value, and that's the value that we're telling the device. We can also do uint8t in b, uint16t port, which reads a value from the device at this specific port. We also need to declare one more function, which is the io_wait function. And what this does is just waits for a little amount of time, because some devices on older machines on the I/O port are slow and we need to wait for them to complete before continuing sending more commands. So now we can jump on over into io.cpp and write those functions. So include io.h, and the first one we're going to do is void outb, uint16 port and uint8 value. And we're going to use inline assembly for this, so asm volatile. We need to declare it as volatile so that the compiler doesn't change anything. It has to be specifically what we write. Bracket, quotation mark outb, %0, comma, %1. Go out of those quotation marks and add in 2 colons. And then we need to do quotation mark A, bracket value, comma, quotation mark ND, quotation mark, bracket port. So we're passing value into this register here and passing port into this register here. So we're putting value out onto this port. The next function is the inB function. So uint 8t in B. And we have the uint 16t port. And we need the return value, which is a uint 8t return val. Now we need our inline assembly, so ASM volatile, bracket, quotation mark in B, percentage sign 1, comma, percentage sign 0, and quotation marks. Now I'd like to go into a new line, so we need to input quotation mark equals A, and quotation mark bracket return val. So we're putting this into here so to signify that we're putting the value into this return value variable. New line, another colon, quotation mark ND, quotation mark, and the port. So that is this register 1 here, which we're putting the port into. Then we can return val. The next function is our IO wait function, void IO underscore wait. And we need some more assembly, so ASM volatile, bracket, quotation mark out B. So what we're doing is sending a value to a unused IO port, so that we just waste one IO cycle, so that any device that we've communicated with has time to catch up. So out B, percentage sign 0, comma, $0x80, which is the port that we're using, colon, quotation mark A, bracket 0. So we're sending 0 to port 80. That will just waste a single IO cycle. So as I said, any device has time to catch up. This needs to be 2 percentage signs, and instead of 0, it needs to be AL. Alright, now that we have those IO functions, we can go about remapping the PIC chip. The PIC chip needs to be remapped so that the interrupts that it produces doesn't collide with the interrupts produced by exceptions, because by default, the interrupts produced by the PIC chip span from 0 to F hexadecimal, and that is the range that our exceptions also span, so that's really not good. So to start writing the function to remap the PIC chip, we can jump back into interrupts.h and declare that function, so void remap PIC. And then jump into interrupts.cpp and create the body of that function. So void remap PIC. Now we're going to need to define some variables to make it easier to talk to the PIC chip. So just some basic IO ports and values that we'll be sending over the IO bus. The first of which are define PIC1 underscore command 0x20. And that is the command line of the master PIC chip. So PIC1 is the master, PIC2 is the slave. There's 2 chips. We don't really need to worry about that at the moment. The next one is define PIC1 underscore data 0x21. So this is the data line of the PIC chip. Get rid of those semicolons. That'll ruin everything. Define PIC2 underscore command 0xa0. So that's the command line of the slave PIC chip, and define PIC2 underscore data 0xa1. Now we need to define some data values that we're going to be using to pass to the PIC. So define ICW1 underscore init, which is 0x10. Define ICW1 underscore ICW4, which is 0x01, and define ICW4 underscore 8086, which is 0x01 as well. Now in interrupts.cpp, we can use those values to talk to the PIC chip and remap it so that its interrupts do not collide with the exceptions. So first off, we need to save the bit mask of the PIC chip. The bit mask just masks the interrupts that it sends to the computer, so we can make it so it sends some interrupts and ignores others. So we just need to save those of the master and the slave chip. So A1 equals in B PIC1 underscore data, IO underscore wait. We need to wait so that it catches up on some systems where it's slower, as I said. And A2 equals in B, PIC2 underscore data. And we're going to need to include io.h so we have access to these IO functions. So include //io.h. And now after getting A2, we need to do io underscore wait again. Now we need to initialize the master PIC chip. So out to be PIC1 underscore command, comma, ICW1 underscore init, or ICW1 underscore ICW4, IO underscore wait. Now we need to initialize the slave PIC chip. So out to be PIC2 underscore command, ICW1 underscore init, or ICW1 underscore ICW4, IO underscore wait. Now we need to tell the PIC chips their offsets, their interrupt offsets, so that it doesn't collide with the exceptions. So we're going to set the master PIC to 0x20 and the slave chip to 0x28. You don't have to use these offsets, but I'm going to use them. So these offsets correspond to which entry in the IDT are called when the PIC triggers these interrupts. So out to be PIC1 underscore data 0x20 IO underscore wait. Then out to be PIC2 underscore data 0x28. Then IO wait. Now I need to tell the two PIC chips how they correspond to each other so they know of their existence. So out to be PIC1 underscore data 4 IO wait. Then out to be PIC2 underscore data comma 2 IO wait. Then we need to tell the PICs to operate in 8086 mode. So out to be PIC1 underscore data ICW4 underscore 8086 IO wait. Out to be PIC2 underscore data ICW4 underscore 8086 and then IO wait. Now we need to restore the bit masks that we saved at the very beginning. So out B PIC1 data A1 IO wait, and now out B PIC2 underscore data A2. Alright, so that's our PIC remapping function. Now back in kernel util.cpp, we can call that function after we load the interrupt descriptor table. So remap PIC. Now the next thing we need to do is create a handler. So the next one I'm going to be creating, and the first interrupt we're going to be enabling on the PIC is the keyboard. So we need to create a keyboard handler. So we'll jump back into interrupts.h and copy our GP fault handler and change that to a keyboard handler, or a keyboard interrupt handler. Now in interrupts.cpp, we can copy one of our fault handlers and rename the function to keyboard int handler. And what we can do is, when the keyboard button has been pressed, we can do global renderer print pressed. And get rid of this, make sure there's no while true so that we can return as well. Now we need to unmask the keyboard interrupt inside the PIC. So back into kernel-util.cpp, we can do out b, we need to include io.h, include io.h. So out b, our PIC1 underscore data 0b11111101. So we are unmasking the second interrupt, and we just make sure that all of the PIC2's bits are masked so nothing comes through there. Now to enable our maskable interrupts, we need to do assembly, inline assembly, STI. So STI just enables our maskable interrupts. Alternatively, if we want to cancel it, the command is CLI, but we don't need to cancel it right now. Now back in kernel.cpp, we can remove this page faulting code, and in interrupts.cpp, we can stop the page fault handler from causing a page fault. Now we can compile and make the image and then run that, and then see if we can press a button and get the renderer to display this string to the screen. Okay, so we've got a general protection fault, so it's clear that our interrupt handlers are working. The problem is that we didn't add our keyboard handler into the IDT, so we'll copy our GP fault and change it to int keyboard. Replace all the references to GP fault and change the offset to, well, the keyboard is the second interrupt and we've remapped it to 0x20, so that's 0x21. So the first interrupt will be 20, but we need the second, so 0x21. And the handler is the keyboard int underscore handler. Now, as you can see at the top left, kernel initialized successfully, and then I'll press a button and it displays pressed to the screen. However, if I keep pressing, it doesn't continue displaying pressed on the screen because we need to signal to the keyboard that we've handled the interrupt correctly. So let's do that now. Back in interrupts.cpp, we need to read from the keyboard IO port to signify that it is ready. And we also need to tell the PIC chip that we need to end the interrupt. So the first thing we'll do is uint8t scan code. So we'll save the scan code of the keyboard, so inb 0x60. That's the port that the PS2 keyboard is located on. So we'll save the scan code. We won't do anything with that yet, but we'll save it because we need to clear the keyboard's buffer. And now we need to make a new function, which is ending the interrupt for the PIC chip. So back in interrupts.h, we can declare two more functions. Void PIC underscore end master and void PIC underscore end slave. So if the interrupt is generated by the master PIC chip, then we need to call end master, otherwise we need to call end slave. So that's fine. Jumping back into interrupts.cpp, we can write the bodies for those functions. So that's void PIC underscore end master. So we just need to do out b pic1 underscore command PIC underscore EOI, which is end of interrupt. We haven't defined this yet, so let's define that now. So in interrupts.h, we can do define PIC underscore EOI, and this is 0x20. So that's the value we need to send to these ports. So to end master, we do pic1 underscore command PIC EOI, and for void PIC underscore end slave, we need to do out b pic1 command PIC EOI, but we also need to do with the same with the pic2. We'll do the end of interrupt for the second chip before the first one. So we out b to pic2 end of interrupt, and then we out b to pic1 end of interrupt. Then inside the keyboard interrupt handler, we just do PIC underscore end master. So now we should be able to press our keys as many times as we want, and it will continue to display pressed to the screen. Alright, so we have kernel initialized successfully, and now I'm going to press some buttons, and as you can see, it continues to display pressed to the screen. So our keyboard handler is working correctly. Alright, so that will be it for this video. In the next video, we will be turning these key presses into actual letters, and we will also be writing a mouse interrupt handler. As always, thank you for watching, and I will see you next time.